Okay, Royals. For lesson 5.8, the derivatives of the natural logarithm, just want to quickly review the shapes of these graphs. In 5.7, we discovered the natural base, an exponential function, and a function who is equal to its own derivative. When we look at the inverse of that relationship, so call this f, you can call this f inverse. We could just define it by its own equation now, y equals the natural logarithm of x. And if we visualize the rate of change underneath here, we're looking at a function whose rate of change grows without bound as x approaches 0 from the right, and the rate of change approaches 0 as x increases without bound, which will work nicely as a bit of a memory aid for us that the derivative of this expression is the reciprocal of x. Notice that the natural logarithmic function has the natural restriction that x has to be greater than 0, so we wouldn't need to go out of our way to say that. Here, often we will be required to say x has to be greater than 0, although we usually don't worry too much about these restrictions in our course. I just want to point out that we've actually satisfied a need that perhaps we didn't recognize we had. And it's a need that sort of touches a little bit on the second side of calculus, on Leibniz's reason for developing calculus, which isn't so much studying rates of change, but studying areas underneath curves. It's a branch of calculus that you'll see towards the end of a first-year calculus course, where you take the antiderivative. You're given a function, and you need to figure out an original function that would have that function as a derivative. So if we take a look at maybe our list of polynomial functions, let's say if we had a derivative function that was x squared, by just sort of undoing our exponent rules, we should be able to figure out that the original function would have been in the format 1/3 of x cubed. So that the derivative of 1/3 of x cubed would be 3 times 1/3 times x to the exponent 2. We would, of course, have this constant here, this unknown constant, that I'm not entirely sure what it's going to be. It could be any number here. Usually I would be given a clue about the original function. Okay, back to our goal. If I want to find a function whose derivative is a linear function, then maybe you can tell me that the original function would have to be 1/2 of x squared plus some constant term. And that way, when I take the derivative of the constant term, it would be 0. And the derivative of 1/2 x squared would be 2 times 1/2 times x to the exponent 1. Let's keep this pattern up. We get, if we wanted dy by dx to equal 1, then our original function would have been just a linear function with a slope of 1 and any y-intercept at all. Okay. So here's the need that we're not sure we really had. If I wanted to find a function whose derivative was the reciprocal of x, notice the pattern here in our exponents of x decreasing by 1. And this pattern is going to break because I mean, if I continued this pattern, it would look like it would be a degree 0 polynomial function. And that's not the case. So there's a weird, I guess, break in the pattern here. And what we have found is that there is a function whose derivative will be x to the exponent -1, or the reciprocal of x, and that is the natural logarithmic function plus any constant. Okay, this idea of antiderivatives or integration, again, is the second side of calculus that I'll leave your, well, it's not in our curriculum. It's like I said, it's a first-year calculus topic. It's also, even if you're not going to be continuing in mathematics, it's very useful in physics and chemistry.